This is Professor Mark Barkey, and this recording is for my class in Applied Finite Element Analysis. And this is a follow-up to the natural frequencies analysis that we did, and in particular we looked at a beam. One of the things that I always ask my students to do is to do something beyond what I've done in the video. And so some of my students have taken the beam and made it shorter and calculated natural frequencies. And one of the problems that some of the students encountered was something called hourglassing and shear locking. So I want to highlight this and show how you can recognize this and overcome this issue. And as part of this, we're going to do the natural frequencies of a cube. So instead of having a long, slender type beam shape that we're going to analyze, we're going to look at a cube. So that'll highlight this issue with this hourglassing in the finite elements. There's a few ABAQUS features we're going to take a look at. I'm going to bring in my old file from the old version of ABAQUS CAE. We're going to go through the upgrade process. We're going to learn how to unlock a part after the upgrade, make some adjustments, regenerate the part, run it, take a look at this hourglassing and shear locking. We'll talk about that in a little bit. We'll be able to use something called enhanced hourglass control to get rid of that for the most part. We're going to look at the files that are generated during an analysis and what we would want to archive during the analysis. We're going to look at the keywords manual, and we're going to also compare the calculated natural frequencies of a cube that we come up with a journal paper that has been published dealing with the natural frequencies of a cube using the Ritz method. It's another numerical technique. It differs from the finite element method, but we can do our comparison for the first few natural frequencies of our cube. Alright, so I'm going to go through and I'm going to start up ABAQUS CAE, but before I do that I want to take a look in my temp folder and kind of show you what I have in there. So here's my plugins directory for my material properties and so forth that we used on a previous analysis. And then this is my old file from back when I looked at natural frequencies of the beam. I called it nf1.cae. That's actually an old version of ABAQUS CAE that was used, and I don't even have that installed anymore. Okay, so I'm going to get in here. Again, I use open shell, so my display may look a little bit different than yours for opening this up. But I'm going to go into Established Products 2020. I'm going to open up CAE. Now, this has come up in class, and I want to explain this issue as well because I didn't have this issue a few years ago when I made the original videos. In some cases, you can just run ABAQUS CAE directly from this prompt when you are in the administrator menu, in an administrator account. In some instances, even if you're an administrator account, ABAQUS CAE just won't start properly. So it says something like permission denied to the folder. So what you can do is you can right click on this and you can run this as administrator, and that'll take care of that issue. All right. So for whatever reason I have this issue on one computer but not on this one. So I'm just going to click on the ABAQUS CAE and it'll check out a license. As a reminder, you need to make sure that you're connected to the UA VPN for this. So it has this window. I usually just X out of this, but there's some things you can do. You can open your database from here and so forth. I have two screens, so I'm going to move this over to here. And you can set your working directory, or since I'm just using the temp, I'm going to open nf1.cae and let's see what it says. Alright. It says there's no journal file. Any changes will not be recoverable, and we're going to dismiss. Okay, so I must have grabbed, let me make sure, let me close this one, and let me get one that has to be upgraded. Alright, so I had run through this previously, and I must have overwritten the file. So this is the one from a few years ago, the nf1.cae. So let's try this again. I'm just going to open this. Okay, so it's from ABAQUS CAE 2016, The database must be converted to the current release, which in this video is 2020, before it can be opened. Do you want to convert the database now? And so I'm just going to select yes. So every version of ABAQUS, we can look at the conversion log, every version of ABAQUS is slightly different in the format of the file. It can recognize what version of file it is and automatically convert that to the upgraded CAE database. Usually this is pretty painless. One of the things we're going to talk about is what files you should keep and might want to keep for a future analysis if you want to look at something 1 year from now, 5 years from now, or whatever. Okay, so we'll take a look through there. All right, so let's go back in our temp folder and let's see what's in here now. All right, so here's what happened, and this is why I opened the file up incorrectly the first time. It renamed my old nf-1.cae to nf-1-2016. So that's the 2016 version of the file. And now it has saved it in the 2020 version, which is called nf-1.cae. As part of this, here's that log of the upgrade, and it's created something called a journal file. ABAQUS will complain if it can't find the journal file, but it's not a deal stopper. Basically, the journal file keeps track of updates that are made into a CAE file. Alright, so let's get into, let's find our ABAQUS. Here it is. And we're going to take a look. Now, if you notice, there's a lock symbol here on the assembly. And if we get into the part, there's a lock on the part. Okay, so we cannot edit this part right now. So we're going to right click on this and we're going to first unlock this part. And it gives a little warning. The reason why it was locked because it was created from a database upgrade. Unlocking the part will force its regeneration. If the assembly is not locked, it will get regenerated. So right now the assembly is locked. Okay. Then it has a tip, and so we're just going to hit OK to continue this. And so this one, if I remember right, this was I think 200 millimeters long or 400 millimeters long. I can't remember the exact details. I think it was 400. We're also going to go down here in the assembly, and we're just going to go ahead and unlock this assembly. I'm going to get back to our part. And let's see, we're going to try edit. I need to find the right panel here. Okay, here it is. This is the one I want to edit. I want to edit this feature. So I double clicked or right clicked on this solid extrusion 1, and it's at a depth of 400 millimeters. And if we recall from the previous video, the square cross section was 20 millimeters on the side. So I want to change this extrude dimension to be a depth of 20. Okay, and then I'm going to hit OK. And now we see that it's this little cube over here. Now, I'm going to need to remesh this. So I'm going to get into mesh. And we'll seed this. We're going to keep our global size of 2. We're going to hit OK. And then we're going to go down in here and mesh the part. Is it okay to mesh the part? Yes. And there is our new mesh for a cube. And just as a reminder, for our, this is a free natural frequency analysis. We're going to look at the step. We're going to use the Lanczos algorithm, and we want to increase this a little bit, so maybe we'll go to 200,000 hertz. The more compact the object is, the higher the frequencies are going to be that are going to be an interest. So number of eigenvalues requested. Some students had mentioned that you may want to change this value to maybe have 10 or 15 or something like that. It's more reasonable. All the frequencies in the range may give you kind of a long computation time, possibly. So we're going to hit OK with this. Let's see, the initial step, let's see, we're doing a linear perturbation and frequency. Alright, so everything was the same. We can take a look at our material properties here very quickly. Again, this comes from our previous analysis. So here's our mass density, and this is tons per cubic millimeter. We're using the Newton millimeter and second system. Our elastic mechanical properties, modulus of elasticity 210,000, newtons per square millimeter, and Poisson's ratio of 0.3. Just going to cancel out of that because I'm not going to make any change. Now in my job, I am going to make a change to my job. And in this, I'm going to use multiple processors since we can do that. Now the teaching edition can use up to 4 processors. The precision we're going to leave is single precision for nodal output. Up to 90% of the physical memory that's present, that's fine. I don't think we're going to need any echo or anything like that. And then we're going to hit OK. Now we haven't submitted this job yet, even though we've hit OK. And I'm probably going to go ahead and rename this job. So I'm going to call it job-1 frequency-cube 1. Okay. And I'm going to hit OK on that. Now, I'm going to go ahead and submit this job and then pause the recording and let this job run. Right now, when we do this, we're going to see this hourglassing, and we'll talk about that in just a moment. So I'm going to right-click on this and then hit Submit. Oh, you know what? I forgot to do something. I forgot to regenerate my mesh. Okay, so this will cause an error here in just a second. While that is waiting for the error, I need to go back in here in the assembly, in the instances, and I'm going to hit regenerate. All right, let me kill this off, and then I'll try this again. It'll take a second for this process to stop. All right, so that says terminate. So let's go ahead and try this again. Whenever you change the mesh, you need to regenerate the instance. And I had forgotten to do that this time, so now we're going to go ahead and submit it again and see what happens. Okay, so it's going to bring up a warning that there were some old files, but that's fine. We're going to overwrite this. All right, so I think this should work out okay. Once this gets running, then we're going to monitor this, bring up the monitor, and then we'll, like I said, we'll pause the video then. Alright, so I'll expand this out a little bit. And so it's gone through its preprocessor, and now it's actually doing the calculations. So my time says 9:03, so let's see what it shows when I get back. Alright, I'm back a little bit early. I want to show you a couple other things that's going on. If we look in our temp folder, we see a whole bunch of files in here now. Okay, you see this SMA bulk and all of that. That is part of the intermediate files that are being created during the analysis process. The presence of this lock file, the LCK file, that file is due to a job running, and it won't let you overwrite the files with that job running. CID is an intermediate file. The DAT, that'll stay around. Of course, here's the input file that's created, and then there's some other files that are kind of intermediate in nature. There's the ODB file, the output database, and then of course the message file, and then a part file, and so forth. Let's see if we have any progress. Okay, so it's still running. Now this one will take a while because we're getting these spurious modes, and we'll talk about that soon. Let's see if we can bring up the task manager and see what's going on with our memory. So Firefox is actually taking up more memory than ABAQUS right now. This is an ABAQUS process, SMACAE, G main. The CPU, actually my recording software is taking more than my ABAQUS as far as the CPU goes. Okay, so everything seems to be going okay. Let's see if there are any other CAE processes. This has all kinds of stuff in here. Nothing else is really sticking out at me. All these various services and processes that I have running on this computer. If you have a big job, you can usually track it by the memory and of course the CPU usage as well. Let's see if we can get a graphical display of the CPU. Okay, so it is running. Different computers will be able to handle the computational load differently, of course. Okay, so it's completed and it's 9:06. So we were using 4 processors, so that kind of makes it go a little faster. Let's get into here and we'll dismiss this window and right click, and we're going to load the results and get in here into our output database. That's the model database. Here's the output database. Okay, and look at all those frames, 846 frames. Now, we know from our previous discussions that we should expect the first 6 frames to be rigid body motion. Okay. So, in fact, the frequency is 0. We can turn on our contour, and this is a contour of displacement magnitude. And so frame 7 ought to be our first non-trivial frame. Let's take a look at it and see what this thing looks like. Wow, that looks pretty crazy. Let's animate that and see what this is trying to do to us here. Okay, so when I hit that, it goes through all the frames. Let's see, if I hit this one where it cycles the harmonic, it should cycle that. Let's slow that down a little bit. Almost looks like those things are turning inside out. Let's see if we can pause this or slow this down just a little bit more. Right there. Okay. You see that kind of a weird pattern? Okay, that's called hourglassing. Here's a real good example right here. See, it kind of goes in and out right there, and it takes the shape of an hourglass. This is what you would consider a spurious mode, and we'll discuss that a little bit. The mathematics behind it comes from the element formulation and is not the main focus of the applied finite element class. You would probably get into this maybe a little bit more in a theory-based finite element class. Let's go ahead and unpause this and just kind of watch that some more. And so when you see something like this, then kind of red flags ought to go up as to what is going on with that. So it has a frequency that it's calculated, and if we go to frame 8, it's the same frequency. That's not unexpected for a cube. I would expect we'd have probably 3 modes that would all have the same frequency. Here's frame 9. And 11, 12, 13, again similar numbers, pretty close together in frequencies, and just all kinds of weird things going on. So the question is this a good answer? And if it's not a good answer, what can we do to fix this? And the answer to that is this is not a good answer. Okay, so we're in around 50,000 hertz for all of this. And it's hard to find a good looking mode shape in here. You might run across one if it can calculate it or not. This is just weird. We want to see all the mode shapes and kind of run through them. Then we can hit this animate time history, and it'll animate all these different frames. Of course, when you do this in a natural frequency analysis, this means something different than if you do this in a time varying load situation. So this will go through each one of these mode shapes and animate it. So there's the rigid modes, and then there's all of these weird hourglassing modes here. We'll just watch this for a minute and we'll see if we might run across one that looks like a reasonable mode. So far I don't see any of them that look reasonable. We're up to 68, 69, 70 modes. We can speed this up just a little bit. Don't want to go too fast in case I might miss a good looking mode. You kind of see some things that look interesting, but they still have all this this hourglassing. Oh, there looked like one that was okay in there. So somewhere around 200, 180. In fact, let me pause this. Let me take this back to animate harmonic. 168, 169. I didn't think that went quite that fast, but there was one in there that looked kind of interesting that didn't have the hourglassing. I won't drag this on too long if I can't find it pretty quick. I'll either pause the video and find it, or we'll kind of skip it. But I think you saw what I was talking about. There was one that didn't exhibit any of this hourglassing nonsense. Alright, well I can't find it very quickly, so we're going to move on from that. And talk about how to get rid of this hourglassing. Let me bring up another page to look at on my tablet, and we can kind of talk about this issue in general terms too. Alright, so I grabbed a couple images from the analysis, and the one on the left is the undeformed mesh. doesn't look perfectly square because my viewing angle is off just slightly. But on the one on the right shows that hourglassing. So what's going on with this is that there's this element that's got these 4 nodes on the edge that we can see. It's actually 8 noded brick elements, but we can illustrate what's going on in just 2D. So we have these nodes right here, and I'm going to put a little, maybe a X right in the middle. If I can do this right, this square element is kind of turning into a trapezoidal shape. And without getting into the mathematics of it, it's analogous to having a solution to an equation where there are more than one root, but only one of the roots makes physical sense, and the other root, your solver just kind of gets stuck in that spurious root. And in the case of the hourglassing, that spurious root has the same minimum energy configuration as some real root that you really want to find. There's some things that you can do about this. Using reduced integration elements typically helps a lot. There are different formulations of the elements that you can use. And the thing that we're going to do in ABAQUS is we're going to use something called enhanced hourglass control. Now, you don't always see this in your analysis if you're using reduced integration elements. In fact, it's very rare. I've been looking for a good test case to show hourglassing for a while and haven't been able to force one to happen until now. And so this is an interesting case for me. So again, what I've drawn is like one of these elements down here, but you can see the general type of what we call the hourglassing that's going on with those 2 elements. Alright, so to fix this, we're going to go in here. I'm going to save this as a different name. Get back into my model. I actually saved the model, not the output database. Okay, so I'm going to get back into my model, and I need to find my mesh. So we'll get back in here in mesh. We're in the part. That looks okay. And you see here it says assign the element type. We're going to reselect this entire mesh and hit done. And it's going to bring up this panel. Okay, so we're doing a 3D stress standard. We're just using linear elements. That's fine. And we have hybrid formulation, reduced integration, incompatible modes, element controls, and it should have, there should be a specification for an enhanced hourglass control. Let's see if we can find it. Okay, there it is. You gotta scroll down in this panel a little bit. So the hourglass control right now is the default, and there are different methods of hourglass control. Okay, we're just going to click on enhanced. Now we're going to learn how to find out about these different modes of hourglass control by looking at our input file, finding the controls section, and then looking in the keyword manual. All right, so now we're going to hit OK for this. We're going to get back into our instance, and we're going to regenerate it. Okay, remember to do it this time. Everything else looks like we're going to keep it the same, and but I am going to copy this job and make it 2, and I'm going to know that number 2 is the one with the enhanced hourglass controls. We can open up this job and make sure everything else is the same. 4 processors and everything. Okay, so we're good. 4 processors, just make it run a little bit faster. And then I'm going to hit submit. Alright, so the little icon is spinning, so it must be working on it. It is submitted. I suspect this is going to run a little bit faster. Our input file processor has completed successfully, and now it is done. Okay, wow, so that was a lot faster than all of those crazy modes. Alright, so let's see what we get. I'm going to go here, I'm going to right click and load the results. Okay, so now I have 2 output databases open. I'm going to make sure I get in the right one. I'm going to look for the step, look at all the frames, open those first few up. I'm going to put this on. Now again, our frame 0 is nothing going on. That's just our basic cube. The first 6 are the rigid modes. See, the frequency is effectively 0 for these things. And then the first non-trivial one should be at 7. Okay, and let's animate this one. Oh, hit the wrong button. I need to do this animate harmonic. That's what I want to do. Okay, so you see how the points of the corners, to me it seems like the whole cube is maybe twisting a little bit about an axis. And the frequency is 71,938 hertz. Frame 8, we have the same frequency. It looks like it's twisting about a different axis. We should expect 3 frequencies that look identical because we have a cube. We have those lines of symmetry. I see. I guess we had 2 there. Now here's number 9. Here's a different kind of mode. Here's the same one, a different orientation. Okay, there are 3 on that one. Okay, kind of see how it's deforming. So I don't see any weird looking hourglassing going on. Now, we've only looked at the first few frames. Let's go ahead and hit animate the time history, and I suspect we will see one as we go through this. So we'll keep a look on the mode number. All of these look pretty good to me. Of course, this is free vibration, and you know that's a weird looking one. We're getting to some of the higher order mode shapes. You know, you may ask, well, how can you ever have anything that's free? Well, you can actually test something. Oh, there's some spurious modes. You can actually test things in a situation that approximates free. So you can take a slender bar or this cube and hang it by a very thin wire. You can put accelerometers on it, and you can hit it with an impact hammer, and you can determine the natural frequencies in something that approximates a free condition. Now, why do we worry about free at all when most objects are restrained in some situation? Well, some planes are not restrained. Okay. Some planes are, and it's kind of a standard thing to do is to calculate the free natural frequencies to get an idea of where you're at. Now, all sorts of things can alter these natural frequencies, including some structural damping and support conditions and things like that. But knowing these natural frequencies tends to give you the lowest ones and would be your first step in looking for frequencies of concern in say, rotating or vibrating machinery. All right, now that we have some perhaps better information, let's see if we can compare this to something that we know in order to determine if we've made any good result. I'm going to bring over a paper that I found on the internet. Straightforward estimation of the elastic constants of an isotropic cube excited by a single percussion. Okay, so effectively this is free vibration. So you have used something called Ritz's method. Now, if you have taken a lot of math, or if you've taken a class in the theory of finite elements, you may have heard of Ritz or Rayleigh-Ritz. It has to do with variational calculus, and in looking at certain functions that we can model a deformation pattern on, we can come up with an approximate way to calculate, in our case, these natural frequencies and mode shapes. This is a numerical method. Ritz's method is an approximate numerical method. It can be used to form the basis of mode shapes for elements, shape functions for elements in the finite element method. It is a distinct and unique method from the method that we're using in ABAQUS. They're all kind of related. So you're going to use algebra in both cases, but so in that case, variational principles are used in both the Ritz's and the finite element method, but the Ritz's method is a distinct method. And so they're interested in this work, these authors are, because they want to be able to look at a material and come up with elastic constants based on what happens to this material. So they have a table and an equation that we're going to borrow. So it says, for the sake of simplicity, the following non-dimensional frequency is used, and they have a capital omega is defined as pi fl square root of rho g. Okay, so here f is the frequency that we're talking about, measured in hertz. L is the length of each side of the cube. G is the shear modulus, and rho is the density. So we're going to use our numbers that we used for our material properties, come up with this value of omega, and then we're going to look at the first 5 natural frequencies, and they use the Ritz method for different values of Poisson's ratio. Their particular values for omega 1, 2, 3, 4, 5 are shown here in this table to several significant digits. 1.428087 is the first one. Alright, so we have a little bit of algebra to do because we want to solve for f. Let me get my notepad up and we'll take a look at this equation in a little bit more detail. Alright, so there's their equation that they have. I just solved for f, and we are going to put in our dimensions for our cube. And I probably ought to have a sketch of my cube just to have this documented here. Our cube that we're looking at is 20 millimeters on an edge. Alright, so omega is the thing that's in the table. 1, 2, 3, 4, 5, depending on the first 5 natural frequencies. Pi is pi. If we're going to convert everything, let's do it to meters. So I'll have 20 times 10 to the minus 3 meters. I'm going to have the square root of g over rho. Now they did this for an isotropic cube, and so did we. So the shear modulus for an isotropic material can be computed by our relationship E over 2. Let me write it here. Divided by 1 plus nu. Alright. So 210 times 10 to the 9th to get in newtons and meters, divided by 2, divided by 1 plus Poisson's ratio, we use 0.3, divided by the density. And if we recall, the density that we used in the previous analysis of the beam was 7,900 kilograms per cubic meter. Now when we put it in the finite element program, we had to convert this to tons per cubic millimeter. So we're going to take this and divide it by 7,900. Now I've already done this calculation and the coefficient I get when I put all these numbers in here is 50889.66. Okay, so that times the omega is going to give my frequency F. Alright, so let's bring up this page again. And we're going to look at this for point 3. 1.428087. All right, let me make sure I copied that down right. Okay. All right, so I'm going to take that number I just computed, 50889.66. I'm going to multiply it by 1.428087. Okay, I have 72,675. All right, let's go back to our model. And let's look at frame number 7. And it looks like I have here 71,938. All right, so this is FEA, and this is from the paper with the Ritz method. So let's see what we have here. If we take the Ritz as the accepted value, the FEA minus the accepted value divided by the accepted value times 100, I got minus 1.01% difference. Okay, so I'm going to pause the video and I'm going to write down the Ritz versus FEA for the next 5 frequencies, or the next 4, and we kind of see where we stand with our finite element results. Alright, and so we can see a comparison of the two methods here. Now, which one is right? Which one is better than the other? I'm not necessarily saying that the Ritz method is better than the finite element method with the enhanced hourglass control. I suspect if you change the hourglass parameters, you may be able to adjust things and maybe even get closer to what this Ritz solution is. But both of these are approximate solutions. So when you look at this, I would say the fact that we're using two different methods and getting very close numbers is a pretty good sign that we're both on the right track. I won't say one is the exact answer and the other is not. They're both approximate solutions to what's going on here. But again, the fact that they're both in agreement is pretty good. All right, well, just the last couple things to do in here. We're going to look at the input file, and we're going to talk about what these hourglass controls are. It's more than just checking a button within the CAE file, so we want to talk about that. Let's get back into our temp folder and see what kind of files have been created. Maybe we sort this by name. So we have all these files in here for cube 1, and then there's a bunch of files in here for cube 2. And then you find some miscellaneous files. Now here's the replay file. We've talked about that previously. Here's the log file from the conversion. That can be safely discarded unless you want to keep it. The COM file, you can get rid of that. The DAT file, you should probably keep that if you want to maintain a trace of your results. In fact, if storage is cheap like it is today, I'd say just keep all of these files. But here's the log file from the analysis. Here's the message file from the analysis. The output database file. The PRT file is a part file. That can be used to import your particular part back into another analysis. Like if you do a restart job or something like that, it'll look for that. Similarly for the sim file, of course the STA file gives you the status. It's the status file. It talks about the number of increments and so forth that are going on in there. Now, which ones should you keep? Of course, I would keep the CAE file and the journal file. Those two files will capture all the options that you have in your job in your CAE file, and you can change that. For archival purposes, I would also keep the INP file. This is a kind of a nothing on a computer is set in stone, but as close to set in stone as possible. If you don't mess with that input file anymore, that is the exact job that you ran in ABAQUS. You can run this from the command prompt. You can import this into other finite element codes or things like hypermesh. Okay, maybe not all the features will import into a different finite element code, but enough of it, the geometry, the nodes, the mesh in particular, will be able to be imported without a whole lot of problems. I would keep this if you're going to archive your analyses. The reason why I say keep the input file in addition to the CAE file, ABAQUS CAE is kind of an expensive code. We're fortunate that we have a greatly reduced cost for the teaching edition for our class. But if you were to do this as a consultant and use this in a commercial application, ABAQUS is fairly expensive, $30,000 to $50,000 per year, depending on how many seats and tokens you get for your job. Okay, so if you don't have access to ABAQUS, or you don't anticipate having access to ABAQUS in the future, and you still want to see what you did, you wouldn't have any way to open the CAE file, so I would keep that input file. Alright, so there's the deal with the different file types. Now let's open up the INP file for Cube 1 and compare it to the INP file for Cube 2. We'll see what else opens up in here. I'm using my Crimson editor. Okay, there's the Cube 1, and then let's do the same thing for Cube 2. Right, so they're both in here. Let's go down to the bottom. Remember, Cube 1 was the one without any hourglass controls, or at least didn't have the enhanced hourglass controls. Alright, so we have, here's our step, here's our section. Let's go over here. We're going to scroll down to the bottom. We're going to go through the nodes and all that element definition. Alright, so we're at the assembly. Let's find the assembly over in the other file. Okay, here's the solid section and so forth. But let's see the difference. In the solid section here we have controls EC-1. And you see we have section controls. Name is equal to EC-1. Hourglass equal to enhanced. And we see 1, 1, 1. Alright, so we just did that checkbox and this is what we get. Let's find out what these things mean. For that we're going to get into our keyword manual. So we're going to get back in here. We're going to look in the documentation, and as we talked about in this version of ABAQUS, the documentation takes you to a website. You have to log in. Couldn't find that particular page. Let's see, let's get to 2020. I'm not sure why it's taking me there. Let me see. I think there's an old link from a previous install. let's see. I'll have to find out where I was at. 3D experience is not quite where I want to be. I might have been in the wrong version of ABAQUS, so let me try this again. Okay, yep. I just selected I have 2 installs of ABAQUS 2019 and 2020. Alright, so this one looks like I'm in the right spot. We're going to go down to ABAQUS. We're going to look for the keywords, and we said it was section control. Alright, so this is a really important thing to do, is you should really understand what all these different parameters are doing to your finite element program. Yeah, I know I said this kind of fixed our issue here. But we look at this, and it goes through, it says using values larger than the default values for Hourglass control can produce excessively stiff response and sometimes even lead to instability if the values are too large. Hourglassing that occurs with the default Hourglass control parameters is usually an indication that the mesh is too coarse. Therefore, it is generally better to refine the mesh than to add stronger Hourglass control. So maybe this is something we can do as well. Instead of using a mesh seed of 0.2 or 2 or whatever we used, we can change our mesh seed. It has all these optional parameters. So this is a required parameter. Set this parameter equal to the label that will be used to refer to the section control definition. All section control names and the same input file must be unique. So they have all these different things: distortion control, drill stiffness, element conversion, element deletion, Hourglass. Okay, this is one we used. Hourglass equals to enhanced. Default for elements with hyper-elastic and hyper-foam materials. Default for standard, and only option ABAQUS explicit for modified tetrahedral or triangular elements. Okay, to define Hourglass control is based on the assumed enhanced strain method for solid membrane, finite strain, and all this. Any data given on this data line will be ignored for this case. Alright, so all these different things are options that can be used to tweak your Hourglass controls. Now here's the data line to define Hourglass control: bulk viscosity, drill stiffness, so forth. Scaling factor for the Hourglass stiffness for use with the displacement degrees of freedom. If this value is left blank, ABAQUS will use the default value of 1. Suggested range is between 0.2 and 3. Okay. Second thing, rotational degree of freedom in shell elements. Default value is 1. Scaling factor out of plane displacement degree of freedom and small strain shell elements, membrane elements, and so forth. Now, we didn't have any other numbers, so if this value is left blank, we'll use the default value of 1. So this is a scaling factor for linear bulk viscosity in ABAQUS explicit. So here's an important thing to state about all of this. Just because you can manipulate a graphical user interface doesn't necessarily mean that you understand all of these details. So it's really important to talk to an experienced analyst or gain the experience yourself to know what all these different things mean. So I'll leave that as a word of caution. But in our case, for our cube, the enhanced Hourglass controls seem to work very well.